Every industrial counter system, no matter how complex, breaks down into three fundamental layers: physical input, logic processing, and the user interface. At the base is the physical layer. This is where proximity or optical sensors detect real-world mechanical events, like a gear tooth passing or a box on a conveyor. These physical events are converted into 24-volt electrical pulses and sent up to the logic processing layer, the PLC. Here, the raw signals are counted, debounced, and evaluated against our production targets using ladder logic or structured text. Finally, the processed data travels over the industrial network to the HMI, giving operators real-time visibility into machine throughput. The first step in any counter system is selecting the right physical sensor for your material.
Use an inductive proximity sensor for metallic parts. It's highly robust against industrial dirt and oil. For non-metals or longer distances, a photoelectric sensor is required, though it's more sensitive to dust. You must also choose between NPN syncing or PMP sourcing outputs to match your PLC's input card.
Finally, ensure rigid mechanical mounting. Sensor vibration is a leading cause of false counts and phantom triggers.
Before we write any code, we must physically connect the sensor to the PLC. Let's draw the electrical schematic.
Every industrial control system relies on a 24-volt DC power supply. We wrote the plus 24V in command lines to our field device. Here is the critical choice: syncing versus sourcing. If we use a PMP sensor, it sources or supplies 24 volts when a part is detected. Therefore, the PLC input module must be wired as syncing, meaning its common terminal is connected to 0 volts to complete the circuit.
Conversely, an NPN sensor syncs current requiring a sourcing PLC input. Always match your sensor type to your input card configuration.
With our hardware wired, we move to the PLC logic. The most common tool for this is the count-up instruction, or CTU block, in ladder logic.
Let's break down its structure. The TON-TU pin is the count-up input. Every time this input detects a rising edge, a transition from off to on, the counter increments. The 90V or preset value is our target count. Let's set it to 10. The 90 spoofing monitors our current value in real time.
When the current value reaches the preset value, the Q output energizes, triggering our next machine action.
Notice how the rung lights up green when energized. Finally, triggering the R pin resets the counter back to 0.
While ladder logic is standard, structured text or SCL is often preferred for complex math and data logging. In SCL, we don't always use a pre-built counter block. Instead, we manually program the edge detection.
We do this by comparing the current physical sensor input against its state from the previous scan cycle.
If the sensor is true and the previous state was false, we have a rising edge and we increment the counter. Crucially, at the end of the cycle, we must override the previous state variable to ensure we only count once per pulse. Once the logic is written, it needs to be visualized. The HMI is the operator's window into the process logic. To display the count, we map the PLC counter's current value tag, usually denoted as C, directly to a numeric display object on the screen. A critical factor here is tag synchronization and the refresh rate. Setting the acquisition cycle to 215 milliseconds ensures smooth real-time updates. With the tags successfully linked, our industrial counter is fully deployed, providing accurate production metrics straight to the factory floor. The first major pitfall in industrial counting is ignoring mechanical contact bounce, also known as signal noise. When a physical sensor or relay closes, the metal contacts microscopically bounce against each other before settling. Because modern PLCs scan incredibly fast, this millisecond level chatter is registered as multiple rapid inputs, creating ghost counts. To fix this, we implement a debounce timer, or timer on delay, TON, directly in our ladder logic. By requiring the signal to remain high for a set duration like 20 milliseconds, we filter out the noise and capture a single clean pulse. The second major pitfall is ignoring the PLC scan cycle time. Every PLC operates in a continuous reading inputs, executing logic, and writing outputs. If your conveyor is moving at high speed, a sensor might detect a passing part and generate a pulse that lasts only a few milliseconds. If this pulse duration is shorter than your PLC scan time, the signal turns on and off while the PLC is busy executing logic. The counter misses it entirely.
The solution: never use standard inputs for high-speed application. Always route fast signals to a dedicated high-speed counter or HSC module, which processes pulses independently of the main scan cycle.
The third most common mistake is silent but deadly: integer overflow. In many PLCs, the default data type for a counter is a 16-bit integer, or INT.
Because one bit is used for the sign, the maximum positive value it can hold is 2 to the power of 15 minus 1. That's exactly 32,767. What happens when your high-speed conveyor hits part number 32,768? The register overflows, abruptly rolling over to negative 32,768.
Your production count is instantly corrupted. To prevent this data loss, always change your counter's data type to a double integer, or dint. A 32-bit dint gives you a maximum count of over 2.1 billion. For continuous production, dint is mandatory. We've covered the entire pipeline of industrial counter systems. Let's consolidate this into a quick reference cheat sheet you can use on the shop floor.
First, hardware. Always match your sensor type to the material and strictly verify your syncing or sourcing wiring layout before powering the circuit.
Second, logic. Use standard CTU blocks for basic ladder logic, but switch to structured text for complex mathematical tracking and data logging. Finally, the pitfalls. Always debounce mechanical contacts. Use high-speed counters to beat the scan cycle bottleneck, and use double integers to prevent overflow. Take a screenshot of this blueprint. This is your foundation for reliable production-grade automated counting.